Okay, looking alternating current. Okay, looking at phase differences between voltage and current for an LR circuit and an RC circuit. Okay, in both cases we assume that we have a driving current. Well, we have a driving voltage, but we do this in terms of the current. And current is I max times the cosine of omega t. The voltage across the inductor is L times di dt for reasons that you should be familiar with, giving us negative L omega I max sine of omega t. Very straightforward derivative. And ignore this picture and this picture. They were drawn for sine functions. We want to draw for cosine function. But over here now, for the cosine function, we've got the I of t in yellow and the V of t in purple. Okay, the I and V have different scales, so we can draw these with any amplitudes we wish, but we see that the negative sine function, which governs voltage, is 180 or 90 degrees out of phase with the driving, or with the current function, the cosine of omega t, with the voltage being 0 before the current is. So you have a 90-degree phase difference with the voltage being 0 before the current is. And that leads us to the phasor diagram, which I'll sketch real quickly. The voltage function, the voltage phasor, is 90 degrees ahead of the current phasor. And we've talked a lot about phasors, so I'm just going to leave it at that. I'm not going to try to label the diagram or anything. Okay, so for the capacitance, the relationship is that the charge, the current is the derivative of the charge function. We analyze capacitance in terms of the charge on the capacitor. Charge on the capacitor then is going to be an antiderivative of the current function, and it should be clear that this is an antiderivative of this, so that the voltage across the capacitor is charge divided by capacitance, and we just divide this by the capacitance. Now we see we got this L omega here and this omega c here. L omega times I max is the magnitude of the voltage of the inductor. The capacitor has a voltage that's out of phase with the inductor, but we have a positive sign here, so that the capacitor voltage, if it's this purple voltage here, and I usually tend to use a different color, so let's do that with a different color. Let's go to orange. Okay, here's your capacitor voltage. You got to go 90 degrees from the capacitor voltage toward the inductor, toward the current. The current is going to precede the voltage by 90 degrees, which is going to give us a phasor with the omega c governing the length of this vector. So there's your phasor. The idea is simply that as this current rotates around here, the voltages and the current are the horizontal, the projections on the x-axis of the phasors that rotate around here, these vectors, I, VL, and VC vectors. The magnitudes of these vectors are governed by the quantities L omega and omega c. I max being multiplied by L omega to get inductor voltage divided, maximum inductor voltage, divided by omega c to get the maximum capacitor voltage. So that omega L and omega c again govern the magnitudes of these vectors. And when you put these three vectors together, you get a resultant vector. When you put these two vectors together, you get a resultant vector. In this case, a resultant vector in this direction. When you have a resistor, you get another vector that goes in with the resultant. That vector is parallel to the current, and we'll talk about that a little bit. These governing quantities, omega L and 1 over omega c, are called the inductive reactance XL, the capacitive reactance XC. And the reactances act in a way analogous to resistances. In addition to determining phase relationships, these reactances determine the maximum voltage across the inductor relates to the maximum current, and how the maximum voltage across a capacitor relates to the maximum current. If we had a resistance, we would have voltage as I max times R. Well, here we have our maximum voltage. Maximum inductor voltage is omega L times I max, so omega L acts like a resistance. And 1 over omega C times I max, so 1 over omega C acts like a resistance in inhibiting the voltage, the maximum voltage, and inhibiting the voltage function.